Okay, I'm going to provide a few solutions or hints so that you can do your homework. Talking about the practice problems for Chapter 10, Chemical Quantities. For about the first three problems, we're asked to calculate the molar mass. Okay, so for this one, the molar mass of sucrose, C12H22O11. I'd like you to work them the way we talked about in class, and that would be by saying 12 carbon, 22 hydrogens, and 11 oxygens. That's straight from the formula. Now, that's 12 carbons times 12.0 is the number of grams per mole. 22 hydrogens times 1.01, again grams per mole, and 11 oxygens, which are 16.0 grams per mole. Okay? Now we calculate the molar mass, as I've done here, for carbon, hydrogen, and oxygen according to the formula for sucrose. Next, we add all those molar masses together. And we get 342 grams of sucrose, C12H22O11. Now, you can do the same thing for the following. Molar mass for phosphorus, pentachloride, and uranium hexafluoride. Okay? I'll just go ahead and set them up, but you're going to solve these. And that's kind of your hint for the next two, 2A and B. 1 phosphorus, 5 chlorines. 5 times for chlorine, the molecular or the atomic mass units. Same with uranium hexafluoride. And find me that molar mass. Again, on 3, we're doing molar mass. We're talking about potassium, potassium manganate. And again, that's 1 potassium, 1 manganese, and 4 oxygens. And you're just going to work it out and add them together to give me the molar mass. Now, this one B is a little trickier. How many calciums do we have here? Well, I'll work it right over here. Then subscript 3 tells me that we have 3 calciums. Now there's a subscript 2 here outside these parentheses for phosphate. We're going to multiply all of the subscripts inside the parentheses by the 2 outside. So we'll get 2 phosphoruses and 2 times 4, 8 oxygens. Now, calculate my molar mass. That's the first section of this. Just find those molar masses. Next, we're going to move into something familiar. We're given a number of molecules of water. 3.52 times 10 to the 24th molecules. And we want to calculate how many moles of water we have. Now, we have molecules on top right here, and we're going to multiply by a conversion factor. What's it going to have on top? It's going to have moles on top. 1 mole. So that way, moles are remaining in our answer, and we need to cancel the unit's molecules, so I'll put them on bottom. Now, we've learned about the mole and how many represented particles it has in it. And we all remember it has 6.02 times 10 to the 23rd. Molecules cancels, you're left with moles, and it's just a division problem. How many atoms of zinc are there in 0.6 moles of zinc? Well, we want to get from 0.6 moles of zinc. Probably going to have a conversion. And we want to get to number of atoms. Right? Well, if our answer is going to be in the units of atoms, we know we're going to have atoms on top here. And what's the unit we're going to have on bottom to make moles cancel? Let moles cancel here. Now, if we have 1 mole, How many atoms do we have? Insert the appropriate number of atoms per mole. That's the number we've been talking about all along. And calculate how many atoms of zinc we have. What is the mass of 1 mole of oxygen? Well, that's pretty simple. 1.00 moles of oxygen times something, and that gives us, how do we measure mass? Grams. O2. Now, I need a 2 here. It's oxygen. It's O2, not just oxygen. I'm going to multiply by a conversion factor that has, well, let's see, we need grams left over, so it'll have grams on top and moles on bottom, so that moles will cancel. 1 mole of oxygen, what's the molecular weight of O2? Not the molecular weight, I'm sorry, the molar mass of O2. Look at your periodic table, put the molar mass right here, and do the math. And you'll get the answer. I'm going to give you all the answers. I'm just going to show you how to work them. I'll do one of these. Again, we're back to molar mass. Simple enough. How about I'm going to do C, or I'll at least set it up. That's 7 carbons. So we write 7 carbons and 12 hydrogens. 7 carbons. Carbon weighs 12.0 grams per mole of carbon. And hydrogen weighs 12. I'm sorry, it weighs 1.01 grams, and there are 12 of them. And now we just do math, and we add our result, and we will get the molar mass of C7H12, which is exactly how you do D, B, and A. Make sure you're putting them in this form. I'd like to see you writing them one over the other and then calculating your molar mass down here, which will make your percent composition calculation much easier. Okay, for number 2, A, B, C, D, and E, for all of these problems right here, the first thing we have to do is calculate the molar mass, just like we did above. For instance, on A, we're going to have lead and oxygen. And the molar mass of lead is 207.2 grams per mole, and for oxygen it is 16.0 grams. We add them together, we get 223.2 grams per mole. Okay, now I have the molar mass. All of these, that's the first step, molar mass. Second step, we need to get from moles, right here, to mass in grams, okay? And to do that, here's the calculation. If we're given 8 moles of lead oxide, put it over 1, we know we're trying to get 2 grams of lead oxide. We need the molar mass right here. And I've calculated the molar mass to be 223.2 grams per 1 mole. Moles cancel. You're multiplying 8 times this and getting grams. That's the way you'll do this calculation for every single one of A, B, C, D. A, B, C, D, and E. Two and 3, same way. How many grams are in 1.73 moles of dinitrogen pentoxide? First, calculate the molar mass, then go from moles to grams. So, how do we do that? Again, 1.73 moles is how we start. We're going to multiply by the molar mass, which you have to calculate in grams per 1 mole, right? Moles cancel, and you're left with grams. Okay, in this instance, it's grams of dinitrogen pentoxide. Okay, so all you have to do first is calculate the molar mass of that substance, and then multiply that molar mass in grams per mole times the number of moles, you'll get grams. Same thing here on 3. Now number 5 is the opposite. We're going to start with, for instance, grams, 0.50 grams of sodium bromide, right? And to calculate the number of moles, we're going to multiply by 1 mole over the molar mass of sodium bromide, okay? In grams. Remember, molar mass in grams. Grams will cancel, and you will get moles. So where you start these calculations, A, B, C, D, E, for number 5, right here, is calculate step 1. Again, calculate the molar mass, just like you did on the first page. And then 2, do this calculation. Okay? That's for number 5. Let's see what number 6 looks like. I believe it'll be the same. We're trying to get from grams of ammonium nitrate to how many moles, okay? So the first step, again, calculate the molar mass of NH4NO3. There are 2 N's, there are 4 H's, and there are 3 oxygens, okay? So you can calculate that molar mass in grams per mole. Now, you're going to use this in step 2. Step 2, you're going to get from 435 grams of NH4NO3, put it over 1, and multiply by the inverse of this molar mass you calculated back over here, right here. It's going to be the molar mass in grams per 1 mole. Sorry about this, getting kind of messy because I'm running kind of small. NH4NO3, and when you solve, grams is going to cancel, and you'll be dividing 435 by whatever the molar mass is to get how many moles, right? To get moles of NH4NO3. Okay, so those are 2-step problems. What's next? 7. We will need to calculate the molar mass of this molecule. 20 carbons, 24 hydrogens, 2 nitrogens, 2 oxides. That's the first step. Again, shocking, I know, but calculate the molar mass. Then, step 2, start with moles, 0.0465 moles, and you're going to multiply by the molar mass that you calculated in step 1 in grams per 1 mole. Moles cancel, and you'll get some answer in grams. Okay? Number 8. Number 8 is when you're going to have to use this little conversion factor. 22.4 liters per 1 mole of gas. Okay, you're going to start with, that's your conversion factor right there. You're at standard temperature and pressure. This says methane gas, but you don't need to calculate the molar mass. All you need to do is take the number of moles you have, 2.66 moles over 1. You know you want to get a volume in liters. So you're going to be multiplying by a conversion factor that has moles on the bottom so that moles will cancel, and liters on top. And this is when we're going to use our conversion factor 22.4 liters to calculate the volume. Number 9 is just the opposite of number 8. Now you're going to be trying to get from volume, 135 liters, to moles. How many moles? You start with the volume, and you're trying to get to moles. How do you do it? Use the same conversion factor, except on bottom, you're going to have liters, so that liters will cancel. And on top, you'll have 1 mole, so that your units of your answer will be in moles. And we just need to substitute our conversion factor there. What else do we have? 10.3. A sample of a compound analyzed in a chemical laboratory consists of 5.3 grams of carbon. That's a part. That's the carbon part. And 0.4 grams of hydrogen. And here's another part over here, 47.08 grams of chlorine. What is the percent composition of this compound? Let's add all of them together. The mass of carbon, the mass of hydrogen, and the mass of chlorine. That's just the stuff they gave you. And when we add all these together, we're going to get the mass of the whole mass. Let's just call it the whole mass. Okay, whole mass. That's carbon, 5.34 grams. Hydrogen, 0.42 grams. And chlorine is 47.08 grams. Add them all together and we get 52 maybe. There's your total mass. Now, we're doing percent composition. If you'll recall, put the part over the whole times 100, and that gives you percent composition. So, here's your carbon part. So to get percent carbon, you put your part over your whole in grams. And to get your part hydrogen, your percent composition part hydrogen, put your part of hydrogen over your whole. Lastly, with chlorine, put it over your whole, part over whole, and that'll give you percent compositions. Okay, on this one, they gave us the whole right here, 18.35 grams of the compound, and it contains 5.74 grams of tin. It's made of tin and chlorine, so how do we find chlorine? Well, we subtract the tin part from the whole part. Okay? That'll give you your parts and wholes, and then you just use part over whole times 100 equals your percent. Number 3, we're combining this many grams of carbon with this many grams of hydrogen to form something. So these are all parts. This is a part. That's the carbon part. And this part right here, is the hydrogen part. And if you add those two together, you'll get the whole. And then you just put part over whole, and you do that twice to get your percent composition. Right? What's next? From the formula for calcium acetate, calculate the mass of carbon that can be obtained from 65.3 grams of the compound. Excuse me. The first thing we need to do is calculate the molar mass of calcium acetate. That's a calcium. The 2 outside the parentheses times everything inside the parentheses. 4C, 6H, and 4 oxygens. It's 1 calcium. Use the molar masses, or the atomic masses. Calculate the molar mass of calcium acetate. Next, this is your whole. What percent is carbon? Well, take this number that you calculate as the part. It'll be this number right here, and this is the whole. Just put your part over your whole times 100, and you'll get a percent. Once you get that percent, all you need to do is take that percent in grams. You're assuming 100 grams of calcium acetate, and you multiply by, you're going to divide by, basically, whatever percent you get for carbon right here, you're going to multiply 65.3 grams times that percent. And if you'll remember, you're going to have to put that over 100 so you can actually use it. So your percentage of carbon over 100 times the total. Now that'll give you, sorry about the way I'm writing this, that will equal your grams of carbon. Okay. Last couple. This one looks about the same. Take aluminum oxide, find the molar mass. Molar mass. If you're looking at just the grams of aluminum, take that number you get right there for aluminum. That's your part. This is your whole. Part over whole times 100 equals percent aluminum. Now, all you have to do is multiply 25 grams of aluminum oxide, that's a 2 and a 3, by whatever this percent aluminum is, by your percent aluminum over 100 grams. And you will get, remember we're assuming 100 grams, so whatever aluminum's percentage is also how many grams in 100. That's what percent stands for. So you'll have this number right here times 25 to get grams of aluminum. Last few, determine the empirical formulas of each of the following compounds. On the percent composition. First step, assume you have 100 grams total, which means you'll have 7.8 grams of carbon and 92.2. 7.8 grams carbon and 92.2 grams of chlorine. Beautiful. Now, these you have to convert, if you'll recall, into, I'm going to give myself more space, 92.2 grams of chlorine. There we go. We have to convert these into moles. How do we do that? By the molar mass of carbon. Molar mass. Oops, you didn't see that. Molar mass of carbon in grams. 1 mole of carbon weighs how much in grams? Find the number of moles of carbon right there, and you'll do the same thing for chlorine. 1 mole of chlorine should weigh, I'll just go ahead and do it, 35.45 grams. Grams cancel. My guess is you're going to end up with about 2.5. Let's say you get 2.5 here. And this you're going to end up with something else. You're going to end up with 2 numbers. Remember? I'm not going to work them out for you, but what you get here is moles of chlorine, and this is moles of carbon. Now you pick whichever one of these is smaller. Pick the smallest. Then divide both by smallest, right? Then use the integers, they're whole numbers, remember? Use integers as your subscripts. What do I mean? Well, you've got a carbon and you've got chlorine, and those numbers here will be what you get once you've divided by the smallest of these guys. And do the same thing here. Assume 100 grams total. Use your percents, convert it to moles, divide by the smallest number of moles to get whole numbers, and then use those integers as subscripts. Hope that helps. See you tomorrow.